Good morning, everyone, and welcome to the fourth day of the discussion meeting on quantum many-body physics and quantum in the age of quantum information. So we will have three talks today in the morning session. All three of the talks have something to do with the role of measurement and whether in phase transition or with entanglement. We start with the first talk of the day by Arul Lakshminarayan from IIT Madras, and he'll tell us about the role of local invariants in measurement-induced phase transitions. Please.
Thank you very much, Debashish. Pleasure to be here again, and thanks to the organizers, Sthitadhi, Subhro, and Manas for this kind invitation. I'm really sorry to have missed the great talks in the last few days, but I hope to talk with those of you who are still here. I'm going to talk about this work which was done essentially by Saurabh Manna, who's a PhD student of Vaibhav, and I'm kind of involved in that. And it's about phase transitions, which are induced by measurement, which have been studied rather intensively in the last 5 years or so, but especially from the point of view of controlling these critical points by tweaking the properties of the basic ingredients in the circuit. So as I will probably say. So those are the local invariants that we'll be tweaking. So that's the outline. I'll first have a very short introduction to this MIPT, and then go on to the building blocks of these circuits. The important building blocks are those which are creating entanglement. So they are the 2-qubit gates. And there's a particular canonical form of it which highlights or separates the non-local content from the local content called the Cartan form. So I'll talk a bit about that. And of these local invariants which are important, which form a connection to entanglement, I'll highlight the two of them, entangling power and gate typicality. And then, so I'll then discuss the specific setup of the MIPT circuit that we studied and the results. All right, so the entanglement in unitary quantum circuits is what we have in mind, first of all. So we have a kind of a Floquet system, if you wish, but it's not really Floquet in the sense that it's built out of unitary operators, so finite time operations. However, a typical setup of this will be such that these are first of all the qubits in this layer, and time is running horizontally. And you have these qubits being coupled by these unitaries here, 2-qubit unitaries in a brick wall kind of circuit. And they are always on in the sense that here these 2 qubits are entangled by this unitary, and then the other 2 neighbors are entangled in the next phase. But it's not Floquet in the sense that a typical setup of this will be as if all of these are random. So it's also random in time. So it's not necessarily periodic in time. But it could be also periodic. There are some differences. So if you just looked at entanglement without looking at measurements, then a situation like this could ensue where you have a growth of entanglement with time. And this entanglement is just the block entanglement of 1/2 of the qubits with the others, very standard von Neumann entropy of the reduced density matrix. The whole thing is initially in an unentangled state. And so the entanglement grows from 0 to a large quantity, which is then it saturates at that point. So these are for a specific circuits with Clifford elements, so that one can do very large number of spins here. So they are either C0 gates, or they're just single particle gates, single qubit gates, which are part of the Clifford family, which is a phase and a Hadamard. And you can see a growth and a saturation, which is the saturation is increasing with this, and that's the volume law, the sense that the entanglement is growing, the saturation entanglement is growing with also linearly with L. So typically what you have is a situation where unentangled qubits can get entangled. In the best possible case of entanglement, they could become like a maximally entangled state, in which case this entropy is just 1. So for instance, one case where you have a linear growth of such entropy would be when you are just creating a lot of bell pairs like this. scenario where we're going to introduce measurements in these are going to disentangle this entanglement. So this red dot here is just a measurement, and we are always going to be doing a measurement in the standard Z basis. And so that can break the entanglement. So this can create entanglement, this creates entanglement typically, and measurement is breaking these entanglements. So in this kind of a scenario where you have this competition, I think this was perhaps one of the first papers, or maybe the first paper, which pointed out that there is a phase transition in this kind of a situation where if you measure a lot of qubits, an entanglement which was initially generated, which could have been this volume law, large, it's scaling as a system size, can become an area law, in which case is essentially a constant. So, so these curves are for entanglement as a function of system size in this kind of Clifford circuit. And what is varying in all this is this probability of measurement, which is a number of measurements by a number of qubits. So in this case, the probability of measurements is very large in this case here. So it's becoming an area law. Here is a volume law, it's proportional to L. So there is something kind of critical probability of measurements, which could be rather small in this case. I think it's around 0.16, that it transits from a volume law to an area law. So the scenario that is usually followed, or the protocol, is that you start with an unentangled state, you evolve it without any measurements till you hit a volume law, like in this case, and then you start doing measurements. And in fact, you look at the entanglement after a time which is typically twice the system size after the volume law entanglement is reached. And there is a probability, critical probability, beyond which measurement has kind of won the scenario. Okay, so in fact, being an ancient culture, we already knew about MIPT. And that's from this classic case of, I think, I believe it is apocryphal, but the villain in this movie, I think is Ajit, says, Robert, is pile ko liquid oxygen mein dal do. Liquid is a jeene nahi dega, oxygen is a marne nahi. And so is qubit ko circuit mein dal do, measurement is a jeene nahi dega, unitary is a marne nahi dega. So it's this competition that is interesting. Okay, so now we go, rather than looking at the circuit, we're going to look at just the 2 qubit gates which are making up the circuit. As I said, they are typically either, what I showed, that case was Clifford gate, so it's just C0, but, and very specific single qubit gates. But a typical scenario would be also random unitary gates taken from the hard measure. And in that case, the transition probability, the critical probability is around, I think, 0.25 or so, when it transits from a volume law to an area law. But here we want to control this unitary, so it's not a random unitary. But so just some background on 2 qubit unitaries, which are just 4x4 unitary matrices. So there are 16 parameters in this 4x4 unitary matrices. But this Cartan form of this, so this is, you can look at it as a unitary between qubit k and k plus 1. The Cartan form of this is a decomposition of this into local unitaries belonging to the kth qubit and the k plus 1 qubit, the UK plus 1, WK, and WK plus 2. And the central part is the non-local part, which is leading to this. So if you count the degrees of freedom, each of this has 3 parameters, so 3 into 4, 12. So 12 goes into the local description of this 2 qubit gate, and there are 3 parameters in the non-local. So only 3 parameters or real numbers determine the non-local content of this 2 qubit gate, and there's 1 phase. So that will add up to 1 plus overall phase. So that's 1 plus 12 plus 3. And so these 3 parameters are very nicely, this Cartan form gives you this non-local form as a kind of an XYZ model. So this basically is just 3 terms here between spin k and k plus 1, and this is sigma x, sigma x, sigma y, sigma y, sigma z, and the coefficients need not be equal, and those are the critical components. Those are the numbers which determine the properties of this 2-qubit gate, the non-local properties of the 2-qubit gate. And it's sufficient, it's known that it's sufficient to restrict oneself to this range of these real parameters C, so that you cover all the unitaries of this kind, SU or U4 gates of this kind, and they form a wedge, they form a tetrahedron of this kind, and depending on the values of C, you get different non-local gates. And so any 2-qubit gate can be uniquely specified by these 3 numbers up to local unitaries. And therefore, these CI themselves, these 3 numbers, are local unitary invariants. And as we know, entanglement is a local unitary invariant, except that the physical meaning of these coefficients is not clear. So, like for instance, here on this phase space here is the identity operator, which just corresponds to all of them vanishing, of course. So you have the identity case there. The C0 has one of them to be pi by 2 and the other two to be 0. So sigma x has a pi by 2 and the other two are 0. There is a gate called I swap, which is sitting at another corner of this tetrahedron, which is almost, it's like a swap gate, except that the non-corner entries are I. It's also called a double C0 for a reason I'll say in a minute. So that's an important gate in which 2 of these are pi by 2. So sigma x as well as sigma y don't vanish. And then the one at this apex, which is the swap gate, which just interchanges the state of the 2 qubits, in which all of these parameters are pi by 2. So it's uniform and it's pi by 2. So these 3 gates, and in fact these 2 phases, will form part of our set of 2-qubit gates that we're going to take. Sorry? Do we need this? So in a circuit, you may not need it because it will, but a general U4 you will need on both sides. Yes. Yeah, there is a constructive way of finding these parameters. Cartan-Weil basis. Well, it's related to the general Cartan forms of group theory. That's what I know, but I'm not sure about the Weil. Probably. In fact, that's called the Weil chamber, so most likely that's also called that. So that's referred to as the Weil chamber. Okay, so the CIs are local unitary invariants themselves, and we have these 3 parameters, and our sort of goal is to see the role of these 3 parameters in measurement-induced phase transitions. But these raw forms of the CIs are not really amenable to an interpretation, as I said, and there are these combinations of them, which are. So these have been studied for a long time. So this is an entangling power, which was introduced by Zanardi and others in 2000, which is just you take a 2-qubit gate. In fact, it can be any qubit gates, but let's stick to qubits. So 2-qubit gates, and you operate it on a product state, and then you look at the entanglement of that product state, and then you average out over the these unentangled states. If you do this averaging over the Haar measure, and if you take this entropy to be the linear entropy, which is this, then there is a simple expression of this entangling power in terms of these Cartan invariants, C1, C2, etc. Okay, so this combination is entangling power. How entangling can your gate be? For instance, if we take identity, obviously there's no entanglement created, this entangling power is 0. But also the swap gate, which is very non-local, it interchanges 2 particles, is also not creating an entanglement, so the entangling power of the swap is also 0. The entangling power of the C0 gate is the largest possible among qubit gates, and so also is the I swap. Okay, so both of them are 2 by 3, they maximize this entangling power. But this does not distinguish between gates like identity and swap, and this was one of the reasons that we introduced the gate typicality measure, but it's not the reason. So which also has a very simple form in terms of this. It doesn't have a very simple interpretation as the entangling power in this form. But nevertheless, it maximizes, the gate typicality is the largest for the swap operator. It still vanishes for the identity operator. Yeah. Average over these product states. Yeah, so you take these product states and you're asking how much entanglement is being created by this. But now this product states you could just take from the Haar measure on the individual spaces. Yeah, single qubit. Which alpha? Oh, that's just a constant, some scaling. Everybody uses a different alpha. So our scaling is such that this entangling power goes from 0 to 1. 1 is the maximum possible, which is not reached by qubits. Okay, so we'll come to that. Yeah. Yes. You're right. Exactly. Yes. Okay. Yeah. You can interpret it probably as coherence being transformed to entanglement, you're saying. Yeah. Yeah. It's interesting. I don't know how much of that can be put into a general framework. I haven't seen that being. Right. Yes, 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 yeah. That is ancillar assisted entanglement, or yeah. So entangling power with ancillar assisted also has been studied. In that case, there will be a non-zero thing for swap. Yeah. Okay. Yeah. So this is a kind of a phase space, if you wish, of all 2-qubit gates, in which the x-axis is this entangling power and the y-axis is this gate typicality, or GT. Here is the local gates, which are 0 entanglement, as well as 0 gate typicality. The C0 gate is here, which has maximum possible entangling power and some gate typicality. Swap has 0 entangling power, maximum possible gate typicality. And the DC0 or I swap is similar. It has a maximum possible entangling power, but different gate typicality. It distinguishes. And this curve here is the powers of swap. I'll come to that in a minute. And these are all these gates on the Weil chamber as well. Okay, yeah. Sorry? Well, okay, so if given the C's, this is the definition, but that doesn't, but I'll come to another definition. In fact, right here, I'll come to the definition, although that red can't be read. Okay, so boundaries of these, of the Weil chamber, as I said, these are the three points which I've been talking on and on about. The C0, which we all know. The DC0 is called a double C0 or a I swap because it has 2 C0s in it. The swap is 3 C0 operations, as we know. So again, I reproduce the qubit diagram with the entangling power and gate typicality. So here is another definition of entangling power and gate typicality, which is written in terms of this EU, which is the operator entanglement of this unitary U. So you can look at the operator itself as a vector in a vector space and just look at its Schmidt, usual entanglement, but linear entanglement. So that's an operator entanglement. How many operators are involved in a Schmidt decomposition of that unitary operator? So that is this EU. ES is the entangling power, operator entanglement for swap, which incidentally is the largest possible. And this one here, unfortunately, is not very visible, is plus or minus operator entanglement of U times the swap, okay? So that's all that is there. So the entangling power, there is a plus sign here and a minus sign here. The gate typicality is a minus and a plus here. So that's another way of looking at the gate typicality definition in terms of these operator entanglements. So it's just some linear transformations of these operator entanglements, but it has some more meaning, I would imagine. Okay, so I've put this plot here to show also the other gates. So there is this swap and the DC NOT gate. It's connected by a straight line for qubits as well as for any qubits. And those are all the so-called dual unitary gates, which are such that this operator entanglement is a maximum possible. So EU is maximized. So they are the Bell states of operators. So they all lie on this line here. Okay, and this is the line of maximum entangling power, C0 to DC naught. Actually, it's two-thirds. Okay, and then the line, there's a straight line connecting the local to the C0 gates, which we called T-dual, because a characterization of these are such that its partial transpose is also unitary. Okay, so you might think of these things are being just connected by a swap. So if you multiply a T-dual by a swap, you'll go to a dual. And then there's a connection of this is a parabola in the case of qubits. This is the fractional powers of swap. Okay, so that connects this. Actually, the scenario is quite different for qubits and above. For qubits, roughly, this is a picture. You have a straight line. These are the things. But now the T-dual and the dual lines meet. And those are actually operators for which you have maximum entangling power. Okay, they have been called two unitaries because these are such that there are two scramblings or permutations of the unitary operator, partial transpose and the so-called realignment. Both of them remain unitary under this. Okay, so this is just to give you an idea of the, but we're not going to go into qubits. It's really only qubits, and that's the scenario. Yes, please. Yes. Yeah. This one. Which one? Interpret what? Yeah. 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 No. It's some other unitary, so it's not a probabilistic mixture. In fact, a typical state or a hard random would be having an entangling power, I think, of 0.6. So it would be somewhere here. Okay, and it would be in the interior of this Weyl chamber somewhere. Yeah. No, because these are all unitary operators. Convex combinations will not remain unitary. Okay, so the scenario in which we are operating is that we are keeping the non-local content fixed. So in this entire circuit, we have only one non-local operator. So that means that these C parameters for all the 2-qubit gates that we consider are the same. So they are uniform that way. What differs are the single qubit gates, which are hard random. Okay, so this is a scenario which people have studied before in some other contexts, and it's interesting. You can do some more analytical work and so on. And also it provides a control on what is crucial, namely the entangling power of these gates which are leading to this transition in the first place. So, okay, so that's what we'll be doing. We'll be fixing the non-local content and varying the local content. And the question is, how does global entanglement depend on the fixed 2-qubit building block? Only single qubit gates are random. How does the critical probability especially depend on this entangling power and gate typicality? Is there only one universality class, etc.? So yeah, so this work is there in the archive. It's to appear in Physical Review A shortly. Okay, so here are some results. So first of all, our difference between ours and the other usual approach is that we don't start from a product state. We start already from a hard random state. So you can say, why do we wait for the volume law to develop? I'm going to start from the volume law. Okay, although one may ask whether there is truly a volume law in a many-body system, and maybe R is more than a volume law. But we are modulo that, we are going to actually start from a state which has volume law already, and then we are going to put it through the circuit, and we're going to start measuring it, and we're going to wait for twice the length of the qubit, which seems to be enough. We have played around with this to see whether we have kind of stationary properties. And then we're going to look at the block entanglement of one half whether the other. So if you do an average of this overall possible measurement scenarios, for a probability of measurement being 0.2 and for 12 qubits, you get a picture like this where we are plotting the average entropy produced as a function of these two local invariants, which are fixed in this. So for every one of these things, it's fixed. So we take one of these points here, and then we are doing this, we are finding out this average entanglement. That's how we produce this plot. And you can see that there is already a fairly smooth dependence of this entanglement as a function of these local invariants, especially the largest entanglement or entropy is produced in the neighborhood of the I swap or the DC naught. The smallest, not surprisingly, around the identity. The C naught seems to be somewhere in between. This is the dual unitary line. It also seems to be rather high. So this is the average entanglement which is produced after this time 2L. And there is a clear kind of some dependence on these local unitaries. Yeah. Yeah. P is, yeah, yeah. Exactly. Yeah, yeah. Exactly, yeah. I'm coming to that. So, but yeah, just to show, it's still not going to criticality, just to follow some of these lines. Maybe I showed two graphs, one following the line from I to C naught, which is the so-called T-dual gates, and the other from identity to swap, the powers of swap. So this is for the identity to C naught gate. So it's actually that line can be followed very easily by taking fractional powers of C naught. Okay? So this alpha is 1 is the C naught, alpha is 0 would be the identity. So you'll see that the identity is, it's going to the area law really fast, or I mean with this probability, not fast, sorry. This is all for this fixed time. A small probability of measurements is sufficient for you because it's not creating any further entanglement. Whereas the C naught is the largest, yeah. You will get some point here. If you take a hard random, yeah. Unless there's something completely wrong with what Saurabh did, yeah. You can think about it that way. But actually, yeah, what's important is I think that it's not like that would be a difference between 15 and 12, but I think that 3 is important. We're keeping that. Okay, so you can see that the circuit itself is more robust if the basic brick entanglement, operator entanglement is larger. This is for the swap to identity to swap line, which this is the swap. So swap is as good as identity, it doesn't create any entanglement. So alpha is 0 and alpha is 1 will give you, by the way, this is also the fractional powers of swap. So both of them are lying on the same line here. This, which has the most robust, is the square root of swap. These two are for 0.2 and 0.8. So this is closer to identity, this is closer to swap. you can see that actually their entangling power is identical, but they have a different gate typicality. So, and they have very different entropy behavior. So the lesson to be learned here is, in fact, the gate typicality is also important. It's not just the entangling power. Okay, so for this, unfortunately, it doesn't seem to be very, I don't know, at least we didn't do anything very analytical with this, but one extreme case which we should be able to do is where you have only measurements. So you're starting from a hard random state, you have only identity as your 2-qubit gate, and then you only measure. So in that case, one can work out the measurement, the entropy. I don't know whether this is really an assumption or not, but this is what we start with. Suppose we start from a hard random state of L qubits and we measure X of them. Then we assume that the resultant L minus X qubits are also hard random. If you assume that, and so this is actually the page formula, then one can find out what is the entanglement as a function of the probability and the time to which you're making the measurements. And that follows these curves here. And in fact, there is a comparison between analytics and numerics, and they follow very well. Well, the lesson to be learned from this is any non-zero probability of measurement will immediately give you an area law if you don't have any measurement at all. If you don't have any dynamics at all. And that's natural because you're starting from a hard random state. So any non-zero probability, you're going to measure all the qubits eventually, and you're going to disentangle the state. So you can show something like this, the entanglement decreases. In other words, the critical probability is 0 for the case when you have identity or swap, actually. Okay, and this is a case of C naught, which I will highlight in and the others follow in a similar way, that you subtract from this entropy the log L, which is the critical entropy at criticality, and then you look at the entropy, this entanglement as a function of probability. I think this is done in in the MIPT literature. Then you see an approximate crossing point for different system sizes, and then you do essentially a finite scale analysis, scaling analysis with some scaling function of this kind with a critical exponent nu and this critical probability. And we find a pretty decent collapse of this kind here for various system sizes. And the critical exponent is 0.36, so it's much larger than what you would expect for a typical hard random gate. And the exponent is something around 1.5. And now you can do this for not just this corner gate here, but everything around this entire phase space of this. But by the way, I should, in honesty, we have not covered all U4, although we have covered the entire EPGT plane. I'll come to that in a minute, but actually what we have done is we have gone along all these borders, which is important borders, this dual, T-dual, etc., as well as these planes. We have not gone into the interior. Okay? So that's it's quite, it's quite expensive doing this, but I think this is telling you already some interesting things, hopefully. So the critical probability increases from identity to C naught as we are going towards this. So as you're going towards this, so let's follow this table here. So the entangling power, so this is identity, 0 entangling power, gate typicality is 0. If you do numerically, you'll get something like 0.05, which is in the error. So you expect that the critical probability is really 0. And as you go along this line, systematically, your entangling power will be increasing. So here is something which is very small, so close to identity. The gate might be somewhere here, 0.074. Its critical probability is again rather small. So as you're going down this, until you come to hit the C naught gate at this corner, where it's maximum possible, and the critical probability is as high as 0.36. And so that's along this line. So you can see that with the increase of entangling power, this critical probability is increasing in a monotonic way, essentially monotonic. There are some differences which we don't know whether they are error, could be in the error. And similarly, there are these other borders. So this is the maximum entangling power. So this is always the maximum 2/3. What is changing is a gate typicality.
Why is the mu not
New, huh? Yeah. It's quite, I think within error, this is I'll come to that. I'll show you a whole this thing. Okay, the error in the new is larger. Maybe the experts on scaling can tell us that, but yeah, we're not actually sure whether we can stick our neck out and say that there's different universality classes, for one thing. Yeah, so in this, again, so here the critical probability is very large, so the entangling power is large. We are not able to very much distinguish C0 and I swap, for example, although there do seem to be some gates in between with quite large, like 0.4 as opposed to 0.36. And there are some interesting gates here, which are neither this nor that. They're called the B gates in quantum computing. Okay, then the dual unitary line. This is interesting, from swap to I swap. So this line here, so the swap has entangling, oh, this is something wrong. Oh, this is I swap. Okay, let's do the swap to, no, the dual unitary, yeah. So let's start from here, the swap, which has 0 entangling power. Okay, so almost 0 critical probability. And here, this gate is very close to swap, so it has small entangling power, but you can see that the critical probability is very large. So I want to contrast this with a case here near this near identity, where the entangling power is small and the gate and the critical probability is also small. So this kind of indicates that this dual line is in fact very different from the T dual, and even close to the swap, you have very robust kind of gates. And I think this is consistent with general study of dual unitary circuits. Okay, so there is this, so if you try to plot in this, on this plane the critical probability, you get something like this. I wouldn't say it's super educative, but I mean, you do see very large. So compared to the average would be, R random would be somewhere around here, 0.26. You see this region, the critical probability is also very large. It's not just that the entropy is large. The critical probability is large. And around the DC naught gate. There are very small critical probabilities around the identity, but it remains to be seen whether it's a finite size, how it scales with finite size. So there is a phase transition with a clear dependence on 2-qubit LU invariance. There is numerical evidence, we're not sure. So if you look at the universality, if you look at new values, it looks almost uniform here. Looks the same, but there is a difference around the identity gates here. But again, we don't know whether this is something which will survive the large L limit. Yeah. 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 So this is what I was saying. I think it's consistent with, look, if suppose you don't do any measurements and you look at circuits in the neighborhood which are constructed from the swap, it has been shown by Bertini, Prosen, and Koch, I think, that that you will, in the large L limit, you will actually go to a random matrix scenario. So it's completely non-integrable. Although if you do finite size, you will think that there is a transition when you're going from swap to this. But the transition point will be shifting towards the swap. So essentially, the swap is integrable. If you think about that as an integrable point, arbitrarily close to that, in the thermodynamic limit, it becomes random matrix-like. Whereas I think this is a different kind, where, again, I can't stick my neck out, but here it's there could be it may not be a phase transition, but it could be kind of a crossover from a slow Poisson to a Wigner kind of thing on this line. So it's an interesting thing. I think about two kinds of systems which are very close to integrable points. You can go to complete chaos or or gently go towards chaos. I think that is this. So I think this is reflecting that. Yeah. Yeah. That Clifford is only 0.16. So I guess here the locals are playing a very important role, as we know they do. The locals being hard random, they are creating much more entanglement, and it's much more. Yeah, so I wish to end here. And so there are other entanglement characterizers, local entanglements, which I think are interesting to study, like between qubits. Yeah, so beyond qubits, it would be interesting to study gates which have maximum entangling power. Are they, in fact, the most robust? And actually, for qubits, there's a third invariant. After all, I said there's C1, C2, C3. So there are three invariants. We have only studied it for this EPGT. That's sufficient for the gates which we have taken because they are themselves lying in a plane. So two of them determine the third, but it will be interesting to see the third invariant. And actually, the physical meaning is not very clear. I think it has to do with, you can take a unitary operator, map it to a state. So this will be a 4-qubit state. I think the third invariant is related to some kind of multipartite entanglement, something like a tangle for this. So we have to look at that. Yeah, so thank you.
Talk. So I think we have time for a few questions still.
So for the different gates, how does the time depend the rate of entanglement generation with layers?
Rate of entanglement. So you mean with measurements or without?
With measurements or without. So how is it true that more entangling gates?
Yes. So there is, without measurements, there's a study by, I think, Marko Snadrich, where he does, in fact, the same scenario in the sense that he's keeping the 2-qubit gates fixed, as you should if you're doing this. And he does find some scenario like this, where the rates are the largest around here for the ISMA, the rate of entanglement production. Yeah.
How do I physically understand this GT quantity? So it looks, actually from this plot, it looks like if I keep my EP fixed and go up in GT, the entanglement is higher. At least in the sort of bulk.
Entangling, yeah.
But that's not entirely true if I sort of move to slightly smaller values of EP. Right. So, for example, if I take EP to be very small, so 0.1,
right,
and then I sort of go up in GT.
Yeah, you're right. Yeah.
So, how do I sort of physically understand the effect of GT on a
Actually, even without an extended circuit, I'm free to confess that GT has, we don't know what is, I mean, here EP has some average entanglement production thing. GT, we are not 100% sure about. Actually, we came to it in a different way, which I think is, it'll take me some time to get to that. So, but I think honest answer is I don't know. Okay, what is the physical meaning of GT? Although there's been some more works recently with this quantity. Where is that? Yeah, so this work here, you can look at that for some more idea of this gate typicality and why we really introduced it here. But just naively, so what it's doing is it's distinguishing a unitary and its partner, which is just multiplied by a swap. So it's doing that, and what it may be related also to kind of things which was mentioned about ancilla assisted entangling power, but we don't really know. I think I would say that yeah. Sorry.
We have a question there.
Yeah, Arul.
Yeah.
So this regarding this terminology, I have some little bit problem. This entangling power, I understand that the entangling unitary and non-local unitary. Are you using the synonymous way?
Non-local.
Non-local power or non-local strength of unitary or entangling strength of unitary. Entangling
So
strength.
no. So non-local. I mean, as in a Schmidt decomposition.
Yeah.
You would have more than one term.
Yeah. Now regarding this GT,
Yeah.
I'm trying to say, you see, the C0 gate. If I take, I'm seeing this as a black box.
Yeah.
Alice has some input and Bob has some input because they are distance parties and C0 is there. So if Alice put plus in her input and she put, Bob put 0, then entanglement created. Now let's say instead of plus, Alice give Kate 0, then it will be final state will be 0, 0. If she put Kate 1, it will be 1. So you have you see a communication power is coming. So that means a non-local strength of a global unitary, it can have an entangling generation capacity
Absolutely.
as well as a
Absolutely. So I think that viewpoint was studied first, in fact, probably by Linden and Chirac. How much entanglement, what's the maximum entanglement that can be produced non-locally? So that way the swap will be creating the largest you can create.
No, but for swap you need the ancilla.
Yeah, with ancilla.
I'm not bringing ancilla here.
Okay.
But you see, without ancilla also, some input, it is creating a communication.
Right.
So you see, now swap has this communication power.
Yes.
Now, whether GT somehow captured that feature or not.
See, but as you say, that's GT is maximum for swap. So if you say that the swap also has 0 communication thing, I don't see that.
Swap has actually communication.
Yeah. So but with ancilla.
No, without ancilla.
Without ancilla. Okay, that's what I'm saying. So that was the Linden Chirac approach. So, but I don't know its exact connection to GT, honestly.
No, GT because it will not be mentioned because it is a sign things, but communication, it will be mutual information, whether some monotone or not, something.
I don't know. I wish somebody would, tell us more. And in fact, even the term gate typicality, we had some debate about why that is so, and I can't even reproduce the.
Okay, we have one last question. Let's take it.
Do things actually depend on your initial state? Because it's if you do a long time thing, it should be some ergodic dynamics, right? On the isn't it some it's a stochastic dynamics on the Hilbert space, and it shouldn't depend on initial conditions. Isn't that?
Yeah, it shouldn't. So I mean, we have taken a Haar random. If you don't take a Haar random, but take some product state, also you should get the same thing, but you should just wait for that much time for the volume law to develop. And there is a issue with that, and that's why we took the Haar random, in the sense that if you start from states which are, operators which are, let's say in this neighborhood, especially, maybe not in the swap neighborhood, maybe here, you may have to wait for a long time for it to thermalize. It might still, but you might have to wait for a long time. So if you follow the typical, usual protocol and you wait for some time, since you're not taking Haar randoms here, I think the time for it to reach a volume law itself would be very, and so that will have to be taken. That's why we took Haar random to start with. Then we are uniformly starting with a volume law for everything.
But then eventually, if you're going to the area law phase, but then it would still take a long time, right? Or from volume?
No, the measurements are independent of that, so it's taking care of that.
Okay, so let's thank the speaker once again.
Thank you.